welcome everybody to the Web3 and Security series. Today we have one external speaker, Daniel Lubaro from the Polygon Zero team. He's the author of Plonky 1, 2, and 3. And so today he will mostly talk about Plonky 2, but also focusing a bit on Plonky 1 and Plonky 3. Warm welcome to Daniel. Stage is yours.
Great, thank you. Thanks for the intro. And I'm Daniel from Polygon Zero, and talking about the different iterations of Plonky, which is all work in collaboration with the rest of the Polygon Zero team and as well as external contributors as well. So just to set the context with Plonky 1, with the context here was that we were working on this blockchain called Mirror, which is a succinct chain with that involved all kinds of recursive proofs. There were recursion similar to what Zexy does, and then that's for one transaction, and then there were more recursive proofs to aggregate transaction proofs together. And at the time, we were sort of struggling to figure out how to make this all practical. At the time, there was basically a kind of a standard approach to recursion using cycles of elliptic curves, and this is what Coda, now Mina, implemented, for example. And I think it took about a minute or two. It was pretty expensive, and we just needed something better. So around this time, the Halo paper came out with the what would now be called a folding scheme. I think they called it nested amortization back then. So we thought that was a really interesting path to get cheaper recursion, and we tried implementing Halo and kind of combining it with the Plonk arithmetization. And this gave a pretty good result. We could get recursive proofs in about 10 seconds, but it's still really slower than we'd like. And really the main issue here was that all of the math we're doing is in 256-bit fields and 256-bit curves, and it's just too expensive. Since normal CPUs support 64-bit arithmetic, we have to break it down into many smaller operations. So we need at least 48 multiplies if we're doing like standard Montgomery multiplication. And then the overall cost for us was about 80 cycles per field operation, which is quite a bit. So this is what led us to Plonky 2, trying to figure out how to avoid these large 256-bit fields and really leverage nice small fields instead. And in particular, the small field that we noticed that seemed to have some very nice properties was what we called the Goldilocks field. It's this roughly 64-bit field that has this Solinus type structure that lets us do a more specialized reduction instead of just Montgomery reduction. I think on most CPUs, multiplication takes about 2 or 3 cycles in this field, so it's way cheaper than, say, the pasta field. And it's also very smooth. So if we haven't really leveraged this, but if someone wanted to do like mixed radix FFTs, there are a bunch of different subgroup sizes that could be used there. And yeah, it just has all kinds of nice properties that if anyone's interested in learning more, Remco has a nice note on that. So the challenge with this small field, of course, is that in these cryptographic protocols, we do a lot of things whose soundness depends on the field size. So consider, just as one example, Plonk and Starks and most of these like polynomial IOPs, at least univariate ones, they usually involve some kind of quotient identity test like this that basically says the prover is supposed to provide this quotient Q such that some constraints are satisfied on the subgroup. And we normally check this polynomial identity by sampling a random point zeta, and then we evaluate both sides at zeta and assert that they match. So this gives us soundness like degree over field size, where field size is the field that we sampled zeta from. So normally this would give us degree of something like this would give us soundness error around 2 to the minus 50 if we just use Goldilocks and if we have like a moderately large degree here, which is not acceptable. So one solution is instead of sampling this randomness from the Goldilocks field, we take some extension field of Goldilocks, maybe a degree 2 or degree 3 extension. So now the extension field is at least 128 bits. And now this field size in the denominator becomes much larger. So now we can get at least 100-bit security or larger if we need to. But there is another solution that we can use, which is we still sample zeta from the Goldilocks field, the small one, but now we repeat the check several times. So this way, this is what we call parallel repetition. And for a public coin protocol in an interactive setting, I believe parallel repetition will always cause the soundness error to shrink exponentially with the number of rounds. Someone can please correct me if I'm wrong. That's my understanding. But with the problem is that we're really constructing a non-interactive protocol, which means it's not enough to look at standard soundness. We have to look at what some literature calls state restoration soundness, meaning that if the prover can rewind anytime something goes wrong, they can restore any previous state of the transcript freely, then we still need the same hardness. So in that setting, I think it's harder. It's not as obvious. I believe the soundness error does still come out to be the same. Where it shrinks exponentially with the number of rounds, but it's not as obvious and not a really clean security argument. And there were some doubts about the way we were doing this until it was more formally analyzed in this paper that came out recently. So we have these two different approaches to boosting soundness, one using an extension field and the other using parallel repetition. And Plonky2 really uses both for different parts of the protocol. So there's like randomness that's used in the permutation argument and randomness used to combine constraints in Plonk. And for that, we use parallel repetition. But for the whole Fry protocol, for example, just runs in an extension field. So arguing Fry soundness is very straightforward. The other sort of difference from standard Plonky2 compared to the regular Plonk protocol is that standard Plonk uses arity 3 circuits. So each gate has 2 inputs and 1 output normally, whereas Plonky3 it tends to use much wider arities. In fact, the standard arity is 135. That's kind of our default configuration. So I think this is very powerful because if we just have addition and multiplication gates, then everything has to be broken down into those simple operations. But if we have these much more powerful gates, we can do suddenly complex operations such as interpolation. And this can be very helpful because within a single gate, we basically have 3 linear operations. But if an operation has to span multiple gates, then that no longer applies. So we can just do a lot of complex operations more cheaply in one big gate than we could in many small gates. We also have to tweak the Plonk protocol a bit just because in standard Plonk, there's this one big constraint for the whole wiring argument. And this is basically asserting that this cumulative product has been updated correctly according to this ratio of F and G representing 2 sides of the permutation argument. And for us, here there's F1, F2, F3, but really we would have all the way up to F135 or even higher, depending on the config. So this would be way too high degree. So I won't go into exactly how we deal with this, but basically we just add some extra intermediate columns to store. In general, when we have something that's a constraint that's too high degree, we usually reduce its degree by adding extra columns, and these extra columns store some intermediate results. Yet another difference between Plonky2 and standard Plonk. Standard Plonk has this public input polynomial, which the verifier directly evaluates. So here, xi is the ith public input, and standard Plonk will basically place the ith public input on the ith gate of the circuit. And this can be a bit awkward in implementations. Like, for example, we have to kind of reserve the first k gates for k public inputs, but in our case, we don't really know how many public inputs we have until we've finished building the circuit. So Plonky1 actually put public inputs at the last several gates instead of the first several. But in Plonky2, we did something different. In Plonky2, we sort of recognized that some applications had a lot of public inputs, and usually we want to keep public inputs small. So sometimes it makes sense to hash all the public inputs we have and just publish a single hash instead of the whole list. And we ended up baking in that sort of paradigm. So we always hash the list of public inputs, and the output of this hash is 4 Goldilocks elements. So we always have basically exactly 4 public inputs after this hashing compression step. And since we only have 4 public inputs, we don't really need a polynomial here at all. We can just kind of split it into, we can just like treat it as 4 constants in our constraint system. So it becomes very simple. Another thing I wanted to mention was, Plonky2 is very focused on recursion, and it supports various different modes of recursion. So the easiest is we have some circuit A, which verifies a proof of another circuit B. And this is nice because it's like there's a dependency in one direction only. So we first build circuit B, and once that's completely finalized, and then we have all the information we need about circuit B, then we build this recursion gadget in circuit A using that verification data for circuit B. We can also pretty easily do like multiple recursion gadgets. There's no complications there really. Sometimes we want to do conditional recursion. So for example, if we have like a IVC setup, but there's some base case. So in the very first proof, we don't want to require that proof to verify some other proof. But then in the inductive case, then we do want to enforce that there must be a valid inner proof. So we need a way to sort of disable the verification gadget in certain cases. But what becomes really difficult is when we call it cyclic recursion. So we have a circuit that verifies a proof of the same circuit, and that gets complicated for us because there's this cyclic dependency. And normally when we're putting together this recursion gadget, we first want to know all the information about the circuit. We want to know how many gates does it have, what set of custom gates does it use, and what is the layout of those gates, what's the exact ordering of them, and we also get like the Merkle root of all of the preprocessed data for that circuit. Of course, if we're verifying our own circuit, then we don't really have any of that information until we've finished adding the recursion gadget because the circuit isn't final yet. So this gets tricky because we basically have to guess, like for example with size, we have to guess what the size of our circuit is going to be. And then if we get it wrong, then we go and correct it later. But there's also other modes of recursion supported in Plonky 2. So another one that comes up sometimes is we have a circuit that wants to verify either this circuit or another circuit. Um, uh, so there's basically two approaches to this. One is we could, if we already have conditional recursion, then we can build on that and we can have two conditional recursion gadgets, and then we can assert that one or the other was enabled. But this means that we're duplicating all the recursion circuitry and doubling most of the work. So sometimes we try to coalesce them into a single recursion gadget, and we sort of select the input depending on which circuit we're verifying in this case. But this gets hard because in order to share the same recursion circuitry, these two circuits have to have kind of the same structure. Like they have to have at least the same number of gates because that affects the Merkle proof length and all kinds of other things. So to do this sort of thing, we have to have some kind of normalization process where we have these two circuits that are slightly different. Maybe they have different sizes, for example, but then we normalize them so they end up having basically the same structure. Maybe we add some padding gates that don't really do anything. Maybe we add some custom gates that aren't actually used by the circuit just for the sake of uniformity. And the other really difficult problem with Plonky2 recursion is when we're starting with a Stark proof, because Stark proofs are variable length, right? And we're using these fixed circuits to verify it. But how do we verify something? How do we do basically a variable length computation in a fixed circuit? So the way we end up solving this is we basically go through the whole range of possible sizes for the Stark. So in Plonky2, they're limited to powers of 2. So we go through each possible power of 2 size. And for that power of 2, we for that specific size, we preprocess a recursive circuit for that size. And then once we have all these different circuits for the different possible sizes, then we do some aggregation of those or some kind of conditional either or logic to verify those together. And the real world scenario that we have is maybe even a little bit more complicated because it's just combining all of these things. So in our ZK AVM, we have this aggregation circuit that has it's really nice because it lets us aggregate in arbitrary patterns. We can aggregate in not necessarily balanced trees or fixed size trees, but we can even choose at runtime what kind of aggregation tree we want to use. But yeah, it means that we have this aggregation circuit with two child proofs, and each one can be another aggregation proof, or it can be a transaction proof, or it can be empty. So this involves cyclic recursion. It involves Stark recursion because our transaction proofs are Starks, and it involves this either or logic as well. And now I just wanted to briefly go into Plonky3, which is kind of the next iteration of Plonky2. And the main theme of Plonky3 is more flexibility. So I wouldn't say that Plonky3 is strictly an upgrade or anything like that, but it has a lot more options. In Plonky2, we were basically limited to Goldilocks and limited to Poseidon hashing and so forth, and using Merkle trees. In Plonky3, there are APIs for all of these things, so you can swap out different implementations. For example, if you wanted to try Starks using RSA-based vector commitments or something like that, then that's possible. You can remove the Merkle tree and swap in this other vector commitment scheme in its place. So it just enables us to do a lot more experimentation that wasn't possible given the API limitations of Plonky2. And in particular, we also have some more powerful batching ideas in Plonky3. So in Plonky2, we would often have multiple Starks that get connected together, and we would end up giving each dark its own Merkle tree and its own Fry instance. So the verification becomes fairly expensive because when we're verifying several different Starks, they all have their own separate Merkle authentication paths, and then there's several different Fry instances that get performed. And in Plonky3, we have the ability to kind of roll them all into a single Merkle proof. Even if these Starks have different lengths, we have this sort of strange Merkle proof which has data not only on the leaf layer, but also in intermediate layers. And then we also have this kind of strange variant of Fry that supports a mix of input lengths. So we start with the largest inputs at the beginning, and then inputs that are smaller, we fold in partway through the commit phase of Fry. Yeah, and just to briefly go through some of the different options that Plonky3 supports. So far, we have breakdown, not the full protocol, but the encoding part at least. We have a bunch of fields. We have Goldilocks Baby Bear and this 31-bit Mersenne field that's very fast. And we have lots of options for hashing. We have Poseidon, Poseidon 2, Ketchak, Rescue, Monolith, Blake 3, and we're working on more. Yeah, that's all I have for now, but I'd love to take any questions that there might be.
Thank you a lot, Daniel. Yeah, regarding questions, let's maybe go into the chat at first. I see one question from Sam asking, in what situations would the cyclic recursion be useful?
Yeah, so I think the easiest example would be something like proving a hash chain using a IVC type setup. We actually have a test in Plonky2 just as an example of this. So yeah, this is a case where it's IVC, so we have a single inner proof for the previous the inner layer of the hash onion. But it's cyclic, right? We have to have a circuit that's sort of verifying itself. At least that's how it would typically be implemented. Does that make sense?
Yeah, that's good. Thank you.
Mm-hmm.
Okay, I have a follow-up question on this. Why do you insist on making it cyclic, like the same circuit verifies itself? Is that a constraint? Why? I mean, I suppose you would get maybe some efficiency benefits if you just have like a circuit B verifies circuit A, or this has something to do with the structure of the hash function that you apply the hash function, or I did not understand what actually is being verified in the original A.
Oh yeah. So I was thinking of a iterated hash or a hash onion. As in, I think, for example, Solana uses something like this, although they don't prove it, but they have like a chain of SHA-2 hashes where they take the output and feed it back to the input.
Right, and yeah, then it really makes sense that you don't define a new circuit every time, so that would be pretty annoying. I understand. So it's actually efficient to have the same circuit verifying itself. Smart. If you don't mind, can we go back like not from the beginning, but I do have questions like more starting, let's say, with parallel repetition and comparing parallel repetition to extension fields. And my question is basically, I would imagine that one is more preferable than other. I know you mentioned like examples in the code where you use parallel repetition, for example, for so for the computing, exactly, for permutation argument, right? So the permutation argument and combining constraints, parallel repetition, and for the rest extension fields. But was this because you think that is the most efficient in terms of code? And wouldn't it be easier to have everywhere parallel repetition or everywhere extension field? Also, now that you, I believe stronger in parallel repetition due to the paper you just mentioned.
Mhm.
I'm
Yeah.
not sure if my question makes sense.
Yeah, that's a good question. I think we didn't have very strong reasons. They were more the choices of parallel repetition versus extension field. They mainly had to do with ease of engineering, I'd say. So we had some cases where we prefer to deal with the base field only for the sake of uniformity, because we have these other polynomials that are already in the base field, and we just prefer to have all of our polynomials defined over the base field to keep things uniform. So yeah, that was our reason, which wasn't a very strong reason for using
Yeah, but
parallel repetition.
yeah, I think it is, because the first two, I mean, I think I get it. The first two places where you use parallel repetition, they all have to do with polynomials basically, and the polynomials by themselves, there is no reason for them to be in something else than the base field, and just because of this randomness that comes along, moving everything to extension field, yeah, doesn't seem nice.
Yeah.
I'm not sure what is polynomial identity test. Isn't this like also part of the, like, basically the final, like, checking the final constraint, like everything batched up? So
Yeah, I meant for that sort of identity that we test at some random point zeta, the identity involving a quotient provided by the prover.
and okay, this to me, now that you explained the first two, this to me sounds like would fit nice as well, like to be in a base field, or I'm mistaken?
Oh yeah, that would definitely be an option there as well. Yeah, uh, yeah, I think both are reasonable options, and I can't quite remember why we uh, decided exactly to do it this way. And I forgot to mention, but in Plonky 3, we're we're actually avoiding parallel repetition in Plonky 3 just because it was a little bit less clean from a security perspective, and we just prefer if security is very obvious, if there are no kind of caveats or things to prove about it.
Okay, that makes sense. It still remains for me to read the paper and to understand the security caveats, but thank you for explaining all these cases. If we move further,
Mhm.
I find, okay, actually here, if you can go back to the structure of the gates.
Mhm.
I find very interesting the fact that you use arity 135. So basically, as you said, like in one gate, you would be able to perform like very much more complex operations than the atomic addition, multiplication, or like adding a constant, as you mentioned there. So this means that you basically construct, right, you construct a lot of these specific gates to basically just work with. I wonder actually how hard it is to come up with these specific gates with such high arity. And at some point, like from the design perspective, there should be probably a trade-off where you say, okay, nothing more fits into this gate and everything else fits into another gate that we have to come up with. I just wonder how you design the gates like that.
Yeah. Um, Yeah, it is a bit challenging sometimes. So, and by the way, the number 135 that's kind of the default arity we use, it comes from Poseidon. So we actually have a gate that does an entire Poseidon permutation, and that takes us 135 wires just in order with like one wire per S box. We need 135 wires to do it. Um, so there are also cases where we want to do something simple like just a multiplication, and then of course it would be really wasteful and inefficient to have a gate with 135 wires that's only using 3 of them. So what we do there is we use what we call sort of SIMD gates or vectorized gates, where we have this multiplication gate, but it really repeats several multiplications. So if it only needs 3 wires and we have 135 wires, then we'll we will include what is that 45 multiplication operations together in one gate. So yeah, it definitely gets a little bit more complicated, but we really wanted to not waste any space in our witness. So whenever we have kind of extra space that's not being used for anything, then we try to find a way to utilize it somehow. And by the way, I think this at the time, this choice of sort of wide arithmetizations was sort of unusual, and maybe with KZG it might not work that well because the verifier would have to do a lot of multiplications depending on the number of columns that we have. But I think it works well with Fry to have these wider arithmetizations, and it in fact for example, we have a Ketchak start that has what is it? It has a few thousand columns, so even a whole order of magnitude more than this. It's a Stark rather than a Plonk circuit, but it's kind of the same cost model.
And okay, now it becomes more and more clear to me, because indeed for Plonky 2 you use Fry instead of KZG, and Fry is heavily hash based. And I suppose when you say we use such and such hash function, that those are the hash functions used for computing Fry, right? So when you say we use Poseidon, this is like it has nothing to do necessarily with Fiat Shamir, but it has to do with how you decide to implement Fry with what hash function. Am I wrong? And then you have to arithmetize the hash function that you use itself. So you have to arithmetize that in the circuit. And obviously you prefer to have a gate just for the hash function. And that being the largest cost in the whole system, you can decide to and you have much fewer operations that are like individual operations like additions or multiplication, so it's actually not wasteful. Is that reasoning correct, what I just said?
Yeah, that's all. Yeah, that's exactly right. So we use Poseidon mainly for the Merkle tree that's used to commit to low degree extensions in Fry. But we also use it for Fiat Shamir as well, although that's more of a minor use with not as much hashing there. And then, yeah, in our recursive verifier, as you said, the main bottleneck is hashing. So if we have a single inner proof, then our recursion gadget uses about 4,000 gates, and about 3,000 of those gates are Poseidon gates that are used for hashing. And then the remaining 1,000 are mainly for constraint evaluation, since the verifier is evaluating each constraint at a random point zeta. That's also one of our significant costs. And yeah, I think besides that, there's some interpolation that the Fry verifier does, and a few other more minor costs.
Yeah, okay. So yeah, that was another follow-up that I wanted to have. Basically, this all makes sense to use such high arity gates because the circuit you are using it's part of a recursion. So you have to build in arithmetization for a hash function because yeah, this will be recursive. That's why otherwise probably you would not arithmetize your hash function if you were to just prove one proof, but you do obviously recursion. I could not fully follow so I understood now the argument for the 3000 gates. I did not understand the argument for the other 1000 gates that relate to I forgot, not opening constraints, but proving I don't know, proving something to do with constraints, but I don't.
So thinking back to that polynomial identity test that the verifier checks this identity at a random point zeta, and the right-hand side is kind of the easy side to evaluate at zeta. Z is this vanishing polynomial that has a very succinct representation, and then Q is just basically a single polynomial sent by the prover. But the left-hand side is actually the more difficult side, because the left-hand side is where the verifier really has to kind of apply the constraint logic. If there's, for example, if there's this Poseidon gate that has 100 constraints in it, then the verifier will be evaluating those 100 constraints at a random point, basically.
Okay, this does make sense, and this is then correlated with the fact that in Fry, because of Fry, you cannot batch together all these constraints. You have to evaluate them separately. That is unlike Plonk with KCG, correct?
Yeah, I think you're right. It's been a while since I've thought about the KZG variant, but yeah, I think that sounds right.
Okay, this all makes sense and is very useful. Maybe I should take a break from my questions and allow the rest of the participants to ask their questions. I have more, but yeah, maybe.
Yeah, don't be shy. Maybe Sam or Maxime, do you have any questions?
Yeah, sorry, I just wanted to follow up on that arity slide again one more time. I know you just talked through it, but so just like I'm trying to envision what like the like my equation would look like using like an arity of 135. You know, I'm used to the kind of traditional Plonk where you have like QL, QR, you know, to for the pluses and the times and QM. So with the arity of 135, I guess how does that affect like kind of like my equation and also like with the, I guess maybe I would reduce the number of rows, but I'd have more columns. So how would that kind of affect the computation?
Yeah, that's a great question. So it's a little bit different from standard Plonk because in standard Plonk, there aren't really different gates. At least the way I think of it is more like one gate, and then you have this selector to enable this multiplication term in it, and this other selector to enable a addition term. I think actually I sort of forget the formula now. But in Plonky2, we have these very separate gates, and we have selectors which enable or disable an entire gate. So, for example, maybe I can pull up some simpler example. So, can you see my terminal? Okay.
Yeah.
Okay, great. So, yeah, these are all the custom gates that are sort of built into Plonky2. Maybe exponentiation might be one of the simpler examples. And when we're defining a gate, we mainly define this function for evaluating the constraints given certain inputs variables. And yeah, this is kind of where we emit the actual constraint here towards the end. And here we're giving this expression that should be equal to 0 on the witness domain. Yeah, actually, maybe this is a little messy or a little bit difficult to read, but yeah, we're basically defining this polynomial which should vanish on our witness domain, if that makes sense. And then once we define all these different custom gates, then we have these sort of automatically generated selector polynomials that can, and for us, it's actually a little bit more complicated, but in a simple version, we could just have one selector for each custom gate that's just 0 or 1. It's 1 on rows where that gate has been placed and 0 on other rows. For us, we do something slightly more complicated to try to minimize the number of selector polynomials, but it's the same basic idea.
Okay. Cool. And then this is also amenable to like if I want to write my own custom gate on top of sort of the custom gates that you've written, right?
Yeah, it's definitely can be extended with additional gates. So I guess of the list here, there are a few that are almost required. For example, actually the Poseidon gate is sort of required because whenever we have public inputs, then we always hash them using the Poseidon gate. And there are a few others that are required. Some of them are optional, depending on what you're doing. They might get pulled in. So, for example, if you call a gadget that does exponentiation, it might pull in the exponentiation gate, or it might just use the multiplication gate, depending on the size of the problem and the configuration of the circuit.
Okay, cool. Thanks.
Mm-hmm.
Okay. Thank you. Oana, do you maybe want to continue unless there are any other questions?
I would like to try actually one more question. I think I was asking about this the first time we met with Daniel. I'm still interested about that. So can you talk a little bit more about the treatment of the public inputs? Because you have a different treatment of public inputs than in standard Plonk. And I suppose it again has to do with the fact that you have a basic circuit and then you do recursion on it. So probably the verification has to be actually as efficient as possible. But I'm still trying to understand here. Is it true that what in Plonk are called public inputs, and they can be rather long, and also maybe we don't know the size of the public input ahead. It depends on the instance, of course. So these public inputs from standard Plonk, do they become actually witness in your updated circuit with updated treatment of public inputs? Is that correct?
Yeah. So I'm not sure what terminology would be best. I guess the way I think of it is, yeah, maybe like you said, the original public inputs that were specified by the user, they actually become private witness data. And then the only thing that really becomes public in the end is the hash of that list. So yeah, effectively we end up with only 4 public inputs after hashing. And yeah, I think we basically had 2 motivations for doing it this way. One was that it was just a bit easier for engineering, um, just because in standard Plonk we have to kind of reserve the first several gates for public inputs, and in our setting we didn't really know how many should we reserve until we finished building the circuit. Um, and then the other motivation for us was the verification complexity. So normally the verifier will be evaluating several Lagrange bases, as shown in the formula here, in order to evaluate this pi polynomial at some point zeta. And so I think with this standard Plonk approach, we end up with one public input on kind of emitted by one gate, particularly the ith public input gets sort of emitted by the ith gate in the circuit. But we could sort of think about, what if we broke it into chunks? So maybe we have 20 public inputs, but then we, instead of one big polynomial with 20 terms, maybe we break it into 4 polynomials that each have 5 terms, which wouldn't quite work in standard Plonk because one gate doesn't even have 4 wires, so we can't quite do that. But in some generalization of Plonk, that could work, I think. So I think our approach could be viewed as, we have 4 public inputs, so we could have a pi polynomial of degree 3, or we could break it into 4 smaller polynomials. And if we break it into 4 smaller polynomials, then they're degree 0, so they're trivial to evaluate, or free to evaluate, really. Yeah, I'm not sure if that was a good way to frame it, but did that make sense?
Yeah, it does make sense, but it makes me actually wonder, is there then any good reason not to do this with every Plonk implementation? I just still try to understand, like, if there is something specific with your setup where you use Plonk. Again, I think maybe recursion is the answer here, but maybe not. So yeah, I'm wondering if this reasoning that you have just explained can be repeated every time, independent of whoever is implementing Plonk.
Yeah, yeah, it's a good question. I wouldn't say it's strictly better or anything like that. For example, if we only have 2 or 3 public inputs, then hashing it and then we end up with 4 public inputs is definitely not preferred. But we do it anyway, just to use the same approach everywhere. So yeah, I wouldn't say it's strictly better. I think it's probably better if we have quite a few public inputs. It's kind of nice to condense them and to minimize the verifier work that way, especially if we're focused on recursion speed, then as you said, it's good to minimize the verifier work.
And I think it's maybe in your case there is something else that is happening, but I'm not quite sure about. You said that you don't know ahead basically not the size of the circuit, but kind of how the circuit looks like. So is this because wait, how does this work? Like how do you build like the circuits? Is it so it's not by hand, it's like automatic in some way, and every time the problem itself changes, and that's why you have a different layout maybe for the circuit? Is that correct? Or
Yeah, so in the Plonky2 APIs, there's this circuit builder object, and the user is incrementally building the circuit by adding gates, but also part of that building process involves declaring some wire as a public input. And in Plonky2, these can be interleaved. Like the public inputs don't have to be declared at the beginning. You can add some gates, then declare some public inputs, and then add some more gates. So I think if we wanted to reserve the first k gates for public inputs, k being the number of public inputs, in that case, we would just have to sort of buffer all of our gates. We would have to say we won't actually lay out any gates, like we won't assign any gates to indices until everything is done at the end. And then once all gates have been added and all public inputs have been declared, then now we know k, and now we can do the actual circuit layout. So we just wanted to avoid that engineering effort.
Thank you very much. It does make sense. I think these are most of the questions from my side.
Great. Yeah. Thanks, Joanna.
Okay, amazing. Are there any other questions? Okay. So Daniel, are there any questions for us, or is there anything else you want to say?
Not really, but if anything comes up later, please feel free to send me a message or on Telegram or Twitter or wherever.
Yeah, thank you a lot. We will definitely reach out again, and thank you again very much for coming here, for giving this talk, and for answering our questions. It was a pleasure to have you, and